temperature and pressure using this idea of ideal gas and how the particles inside of a system could move. And again, so we're going to talk only about ideal gas today. We're going to talk about these gas particles and how they're moving, and we're going to relate that to both the temperature and the pressure. And this is called a microscopic view of how how these ideas come about. Before we motivated it via macroscopic things, and now we're going to use microscopic things. So we can think about, we know that the temperature is related to the internal energy as defined earlier, but let's nail that down. So we can look back at the ideal gas law, just looking at the right-hand side, and you can see that you get number of particles times Boltzmann's constant times time. We just talked about the units of each of these, and we can see that you get the units of this whole thing multiplied together equal joules, because the units are number of particles multiplied by joules per Kelvin times Kelvin. Those kelvins will cancel and you'll just get joules. Remember that number of particles is a unitless parameter, even though it should be carried through your calculations to make sure that you are doing things properly. So the total energy is U, and somehow this is related to the temperature, and in particular the temperature times the Boltzmann constant. It has the right units of joules, and so we have to figure out how these things are related. And so I want to point out we're going to use this curly U to represent the total energy. This curly U is not the same as U that we've been looking at before, which is the potential energy. But this curly U does contain the potential energy. So a normal gas, which has internal degrees of freedom and can bump into other gas molecules, will have potential energy. Ideal gases have no potential energy, and so we will not have to consider the potential energy for these cases. And that means that all of its energy is coming from kinetics. So each of these molecules is moving with some velocity v in some direction, which has some speed, and that gives them some kinetic energy. So again, we have this total energy, and since it's all kinetic, then we can just write that it's equal to the sum of all the kinetic energies, which is the far right side of this equation. Kinetic energy of particle 1 plus the kinetic energy of particle 2, and so on for all of the particles. But we probably have something like half a mole or a mole of gas at least that we're talking about. So this is a lot of particles that we're adding up over. It's much easier for us to say, well, we know we can define an average kinetic energy for the whole system, and that's equal to the sum of all the kinetic energies divided by the number of particles. So if we just take that average and we multiply by capital N, then we can get the average kinetic energy. And so we can define the average kinetic energy. We're going to use these triangular brackets in order to define an average of something. So if there's something inside triangular brackets, then you'll know we're taking an average of it. So this thing in the brackets, this K, is the average kinetic energy. So if we say that U is equal to the average kinetic energy, we can define the kinetic energy as equal to 1/2 mv squared, as we said earlier. 1/2 and m are constants for this average. And as you may or may not know, and you can do an example for yourself if you're not convinced, that anything that is a constant inside of an average can actually be taken out and multiplied outside because you're just adding them together. So that means that this total energy is equal to 1/2 the number of particles times the mass of each of the particles, and again we're going to assume that they're all identical, and times the average velocity squared. So this average velocity squared, again, it's in the triangle brackets, which means that it's an average, and it's over the speed squared or the velocity squared of these molecules. And again, we can define this average in our normal way, but make sure that you square the velocities first before you divide by the number of particles. This average speed squared is actually a Gaussian distributed. We're not going to talk about this very much, but this is something that physics is quite good at understanding. We can measure the speeds of these particles. We know that they're Gaussian distributed, and there's some mean velocity or mean speed, which in this case is 50 meters per second. And again, remember, speed doesn't take into account the direction. When we talk about momentum, we will have to take into account the direction of those molecules. All of this is to say that, and we haven't actually proven this, but it is something that you can prove once you know this distribution of the molecules, which is that the average kinetic energy is equal to 3/2 kBt. So this is an interesting property. Each one of these Each of the molecules can be moving in the x direction, the y direction, and the z direction. The kinetic energy in each one of these directions is equal to 1/2 kBt. Because there are 3 directions, we get the total average kinetic energy for the system is 3/2 kBt. And this is a result that is a microscopic result that relates the kinetic energy of the actual particles in the system to the temperature of that system. And it's a very useful quantity to know, and it will come up again for the next lectures for Wednesday.